that's the recording in progress. So firstly, very glad to see everyone here again. This is our 6th lesson, and today we will be talking about more advanced derivative rules. So if you remember or watched the class recording, last lesson we talked about introductory derivative rules, how to find them using the definition of a derivative and stuff like that. And now we will get to derivatives of more advanced functions. So before I go on, does anybody have any questions about any of the homework slides? Because today I was planning on reviewing the intro to derivatives homework, if anybody has any questions about that. So if no one has any questions, then I will get started. But if you do, then please just call out. Okay, then. So since nobody has any questions, I will get started with the lesson. So I will share my screen. Okay. And once again, if at any point you have any questions, I won't really be checking the private chat, so please just call them out, and I will try to answer them for everybody. Okay. So today we will be talking about derivatives that are a bit harder to do or to derive than the previous class. So today we will be doing a lot of very important stuff for calculus. And yeah, today is like a very important lesson. Okay. So for those of you who weren't here or I don't know, maybe haven't had a chance to watch the class recordings yet. So what we did last time was we found formulas for the derivatives of linear and constant functions. And once again, the derivative is just the slope of a tangent line to a graph at a given point. And what we did was we found the formulas for the derivative functions of linear and constant functions. So the derivative of a linear function is just the slope of the line, and the derivative of the constant function is just 0. We then proved several properties of derivatives. For example, we proved that if you scale up a function and take its derivative, then that's the same thing as taking the derivative of the unscaled function and then scaling it. Similarly, if you add two functions and take their derivative, that's the same thing as taking the individual derivatives of both of those functions and then adding them together. So from these two properties, we also did a similar property. We also proved a similar property to this second one, except instead of a plus sign, there was a minus sign. So these are kind of the two main derivative properties that allow us to do a lot of the stuff that we will do in this course. And then we also use the definition of a derivative, so using the limit, to prove this power rule. And this power rule states that if you have a function x raised to any power, whether it be 2, -pi, e, 100, whatever, and if we take the derivative of x raised to that power, basically the pattern is you bring this exponent down as a coefficient in front of the x to the n, and then you subtract 1 in the resulting exponent. So this is called the power rule, and we can use this power rule to differentiate. Differentiate just means to take the derivative of any polynomial or other power function. And so using these three things right here, I talked about last time how we can differentiate any polynomial or power function at any point. The problem is that is the only thing we can differentiate, right? Without any more complicated rules, we can't expand our knowledge to functions such as sine, cosine, exponential functions. We can't expand to any of that. And so in this lesson, we will try to expand our knowledge of derivative rules to those types of functions. So we will once again find formulas for the derivatives of sine, cosine, tangent, and the exponential functions. And then we will also find a handy rule to find products of functions. So so there was one property of the derivative about addition. Well, the same thing doesn't actually work for multiplication. You can't multiply the derivative of two functions together and get the derivative of those two functions multiplied together. That it doesn't work that way. It does for addition, but not for multiplication. So we will find how it works for multiplication in this lesson. And we will be able to tackle derivatives of products of functions such as x squared times the sine of x, e to the x times the cosine of x, or something like that. We will also be able to find the derivatives of compositions of functions. And what this means is you have a function, and instead of the input being x, it's something like x squared or sine of x. For example, sine of x squared, 1 over cosine of x, where the big function is 1 over x, and then instead of x, you're inputting cosine of x. E to the 2x, instead of inputting x into e to the x, you input 2x. And we will have the tools to deal with derivatives of these types of functions after this lesson. And then similar to last lesson, we will use the definition of a derivative for all of this. Okay, so let's start off with the derivative of the sine function. As you know, the sine function looks like a wave on the coordinate grid. If you graph it, it's basically just a wave. And we want to find its derivative. So similarly to how we proved the power rule, x squared's derivative, right? We just use the definition of a derivative. So we have this right here, this limit, and that's the derivative by definition. Now, one very handy rule when we're dealing with trigonometry is the trigonometry addition rule. In this case, the sine addition rule. And this says that sine of two angles added together is the sine of the first angle times the cosine of the second angle, plus the cosine of the first angle times the sine of the second angle. So you have this kind of repeating product sum pattern. And that is this sine of x plus h thing right here. So once again, I'm assuming you are familiar with trig concepts when I'm going to be doing this. And then we subtract the minus sine of x. So one thing we notice is we have sine of x term in both cases here. Now, because this limit is happening as h approaches 0, we are only dealing with the variable h. So the only variable in this limit is h. Anything that has an x, we can treat as a constant. So let's factor the sine of x out. Notice that this right here has a cosine of h. This has a -1, and then we divide by h. And then we can factor the cosine of x out of the resulting product. And then we can split into two limits and pull the constants, so sine of x and cosine of x, out. Again, we're treating them as constants because the limit is as h approaches 0 and not as x approaches 0. So one of these limits might be familiar. So this is the sine of h over h limit as h approaches 0. And if you had a chance to look at the limits homework, this was one of the problems on there. And we proved that this limit in the homework, they ask you to prove that this limit is equal to 1 using the squeeze theorem that we also talked about in the second class lecture. So I will assume that I will use without proof the fact that this limit is equal to 1. It's definitely not an arbitrary thing that I'm pulling out of midair, though. There is a proof for this fact. Okay, so this limit is 1. Then we also have this mystery limit right here. So this will turn out to be some number, and that number times sine of x plus cosine of x will be the derivative of sine of x. So notice that this thing right here is an indeterminate form. That means that if you try the direct substitution, plugging in h equals 0, we get 1 minus 1 over 0, which is 0 over 0. This is an indeterminate form. So a limit might exist, but we just can't find it yet. And to deal with these types of forms, we can algebraically manipulate. For instance, we can multiply both the numerator and denominator by cosine of h plus 1. And the numerator turns into cosine of h squared minus 1, just by the difference of squares formula. And then, of course, you can use the most basic trigonometry identity, the Pythagorean identity. That will be equal to negative sine of h squared. And then in the denominator, you have h times cosine of h plus 1. Then we can split this into two limits. So since sine of h squared is just sine of h times sine of h. This first limit is the same thing as this limit right here, that's 1. And then this limit is no longer an indeterminate form, because on the numerator you have 0, and in the denominator you have 1 plus 1, which is 2. So this limit is actually 0. So this blue limit in total is also 0, because it's equal to 1 times 0. And so this whole sine of x terms cancel, and all you're left with is cosine of x. So that is actually the derivative of sine of x. It's cosine of x, which was a pretty neat fact when I found it out. So does anybody have any questions about how we did this? Because this is an important proof that you should probably be familiar with. Anyone have any questions about this? No?
Wait, question.
Yeah.
So I'm not too familiar with trigonometry, like identities.
Yeah.
Can you or I mean, obviously you're not going to explain it in this class, but
Yeah.
would it be possible to maybe post something on Classroom about this so that I can just learn more about this before starting next class, the future classes?
Yeah. Sorry about that. I will definitely try to post some materials on trig identities. Yeah. So I will post some stuff about trig identities. Yeah. But for now, I'm sorry about this. I will post the recording. So once you have read over the material, you could listen to that again, I guess. But yeah, for now, I'm sorry, but I'm going to use trig identities for the rest of the class. But I will definitely try to upload something after the class ends. Okay. So with that out of the way, using a similar method, try finding the derivative of cosine of x. So I will give you about 5 minutes to do that. No, oops, hold on. I will give you about 5 minutes to do that. Similarly, try to use a definition of a derivative. And when you are done, post your answers in the private chat. Okay, so I will stop my screen sharing. Okay, so I will give about 30 more seconds if you want to think about this problem a bit more. Once you are done, again, just type your answer in the private chat. Okay, so I will resume my share screen and I will go over this right now. Okay, so similarly to the sign, we just rewrite this limit using the definition. And then just like we used an angle addition identity for the sine function, there's a similar one for the cosine function, and that is this thing right here. So they are a bit, they look the same, but they are actually like different. So you have a minus sign here instead of a plus sign, but it's basically the same concept, just an identity, you know. So that's not the most important part of the proof. But most important part is that, or one of the most important part is that we can break this big limit into a sum of smaller limits. So notice that this cosine of x is once again a constant since we are only dealing with h in the limit. So we can pull it out. Then all the terms that have a cosine of x we can write in a new limit. And then we can factor this minus sine of x out. And we have this limit that's left. So once again, this limit we already calculated in the previous sine of x proof, and that we calculated to be 0. And then this limit is 1, as I already mentioned. And so the resulting derivative is minus sine of x. So the derivative of sine of x is cosine of x, and the derivative of cosine of x is minus sine of x. So initially I found it a bit hard to remember the minus sine of x, but so the derivative of cosine of x is not sine of x, it's negative sine of x. Okay. So that's cosine of x. And then another like really basic function. So just now we tackled trig functions basically, right? We will eventually later in this course develop the tools to get all of the other trig functions from those two basic functions. But first, we will deal with another very important class of functions called the exponentials, right? So like 2 to the x power, 3 to the x power, and so on. So using the power rule, we already know how to differentiate x to the a, where a is some number. What about a to the x? So once again, we used our trusty definition of a derivative. We plug x plus h into the exponent here, and then we subtract a to the x. So then by basic exponent rules, we can split this up. And then since a to the x is a constant, not being dependent on h, we can factor it out of the limit. And so the major question is to calculate this limit in terms of a. So what this first initial step is telling us is that the derivative of an exponential function is that same exponential function times some constant. So you scale up or down an exponential function and you get its derivative, which is actually pretty neat. And exponential functions are very special in this way. So now, once we evaluate this limit, we will get something in terms of a, and we will actually be able to pinpoint what this constant is. But first, it will be preferable to simplify this numerator. What we're going to do is we make this substitution. So this substitution seems very weird and arbitrary to make. But once we do make it, the numerator will simplify considerably, as you will see later on. So this thing right here is called limits by substitution or change of variable. So when we have this unmanipulatable limit, a common thing in algebra that you do is swap in a new variable, rewrite it somehow in terms of the old variable, and see if that is easier to manipulate. So in limits, we not only have to choose the right substitution, we also have to choose what this new variable approaches as the old variable approaches 0, or whatever other value it initially approached. So as h approaches 0, notice that we can rewrite n in terms of h as n equals 1 over a to the h minus 1. Once again, this is just by the logarithm properties, definition of a logarithm, and so on. Nothing crazy here. But then if we substitute h equals 0 into this thing right here, we get 1 minus 1, which is 0. So 1 over 0 is infinity. So as h is approaching 0, n is approaching infinity. This function right here has an asymptote there. Okay. Now we can rewrite this new red limit. I will do the computations in red. So the first step is to replace h approaches 0 with n approaches infinity and make this substitution. So we replace all the h's with this hairy logarithm. But now the convenient thing is that the a to the power of log of a cancel out, right? That's just by the definition of a logarithm. So we have a 1 over n plus 1 minus 1 left in the numerator, which is just 1 over n. So we have a 1 over n left in the numerator, which is very nice. The next step is to multiply both the numerator and the denominator by n, simplify the numerator even more. So in the numerator, we get 1. In the denominator, notice that when we have a constant and we multiply it by a logarithm, we can pull it into the logarithm and make it the exponent of the thing we're taking the logarithm of, right? That is just another basic logarithm property. So this n becomes the exponent of this 1 over n plus 1 thing inside the logarithm. Now, another limit property, I didn't actually derive this limit property, but it follows pretty easily from the other basic limit properties on the limits presentation and on the homework. And the thing is, you can pull the limit inside of this logarithm when it's in the denominator. You can do it when it's in the numerator, but you can also do it when it's in the denominator. And you can pull this limit inside of the argument of this logarithm. And when you do that, just call out if you recognize this limit as n approaches infinity of 1 over n plus 1 to the power of n. Does anybody recognize this limit? Because you might have actually encountered this before without knowing it. No one? Okay. So this right here is actually the definition of a very special mathematical constant. And this mathematical constant is E. So we denote it by E. It's called Euler's constant. This is the most fundamental constant in all of calculus. So this isn't an over-exaggeration. Like, this is the one constant you probably should remember. You should also probably remember, so it's like pi. It doesn't terminate. It doesn't repeat. It's an irrational number. It's also a transcendental number. So E is approximately 2.718281828. It's kind of a very easy number to memorize, 2.718281828. It doesn't repeat after that, for all we know, but those are the first like 9 digits. So this limit right here has been calculated, or is the definition of this new constant that we call E. So once we have this E right here, we can use another logarithm property. 1 over log base A of E is the same thing as log base E of A. And this constant E is so special that a logarithm base E has its own special name. It's called the natural log, abbreviated as ln. So when you see ln, that means logarithm base E. So we finally got to the fact that this limit right here is equal to the natural log of A. We can just plug this into the limit, and we are done. So this is the constant that we scale the exponential function by to get its derivative. Now, the really cool part, so it's already cool that these exponential functions and its derivatives are proportional to each other, but what's really cool is when they're equal to each other. And that happens when we plug in A equals E. Because when we plug in A equals E, we have the derivative of E to the X equals E to the X times natural log of E. But natural log is logarithm base E. So logarithm base E of E is just 1. And so we get that this function, E to the power of X, is its own derivative. So it's primarily this fact, not this cool limit thing right here, that makes E the most important constant in calculus. So this fact right here, we will use a lot. This function is its own derivative, and it is the only function in math that is its own derivative. So this function and constant multiples of this function. So for instance, 2e to the x is also its own derivative. or 0 e to the x is also its own derivative. But these functions, constant multiples of e to the x, are the only functions that are their own derivative, which is honestly pretty cool. Like that is something really neat. Okay, so we found a general rule for exponential functions and this very special function e to the x. So now let's practice a bit. So find the derivative of e to the x plus x squared plus 2 cosine of x minus 5. So to do this example, we would take the derivative. And once again, we can break this up into smaller chunks, smaller derivative chunks. So the derivative of e to the x, that is just itself, e to the x. Derivative of x squared, we use the power rule to find that last class, that's 2x. Then 2 cosine of x, the derivative of that is minus 2 sine of x, because cosine of x, the derivative of that is negative sine of x. And then the derivative of a constant is just 0. Okay, so now you can see that we have the tools to find the derivatives of a much larger array of functions. But the thing is, we still can't find the derivative of e to the x times cosine of x, or x squared times sine of x. We can't find that yet. We can't find that function's derivative. So we have this very handy thing in mathematics called the product rule. And this relates the derivative of two functions multiplied together. And no, that is not equal to the individual derivatives of those two functions multiplied together. So this doesn't work the same thing as the addition rule does. So once again, to derive this product rule, just like we derived the addition rule, we will use the definition of a derivative. So we just plug in x plus h into here. I'm treating this f of x times g of x as one single function because it is one single function, even though it's also a product of two other functions. So you could just plug x plus h into the argument of this big function. Now, this looks hard to algebraically manipulate. So what we do is we subtract and add the same thing from the numerator, and this will make it easier to manipulate. So we subtract this thing right here, and we add this thing right here. So I personally do not know how whoever invented this product rule thought up of this. It seems pretty hard to think of this just by yourself. He probably noticed some sort of pattern and found substitution that will make this work. But this manipulation actually does yield a fruitful result, because from these first two terms we can pull out the f of x plus h. And then from these last two terms, we can pull out the g of x. Once again, this is all happening within this limit. And then this big fraction is equal to the sum of these two tiny fractions. And we immediately recognize this thing right here and this thing right here. So by another limit property, we can split this up into sum of the products of limits, right? Pairwise product. And this right here, right, that's just f of x, because f of x plus h, as h approaches 0, just h, it doesn't matter here because h is basically 0. And so this limit right here turns into f of x. This limit right here is just the derivative of g of x. This limit right here is also just g of x because it doesn't even depend on h. And this limit right here is f prime of x again. And so the derivative of two functions multiplied together is equal to this very neat pairwise sum, so pairwise product sum. So you have f of x times g prime of x plus g of x times f prime of x. So one function times the derivative of the other function plus that other function times the derivative of the first function. So this is something really important in math. It's called the product rule. You will 100% need to memorize this. It's also probably will be good to memorize the proof, because although it is quite easy to remember after you have used it a couple of times, in case you do forget it, knowing the proof and derivation is kind of useful. And so yeah, this is the product rule, and we finally have the tools to deal with multiplying two functions together and taking the derivative. So one example is finding the derivative of x squared times the sine of x. So what we can do is we can say, okay, so this is obviously a product of two functions, x squared and sine of x. And individually, we know how to differentiate both. So when we multiply, we can use the product rule. So this is the derivative of one function times the other function, plus that first function times the derivative of the second function. And then when we expand that product, this derivative of x squared turns into 2x. This derivative of sine of x turns into cosine of x. And that is the answer. That is the derivative of this thing right here. If you plug in x equals 0 into this equation, whatever this thing is equal to at x equals 0 will be the slope of the line, of the tangent line to this curve, which is pretty neat. Now, it seems kind of like a silly example. This should seem like a silly example because we already know how to find the derivative of x to the 5th using the product rule. Oh, sorry, using the power rule. It's sometimes hard to get those two not mixed up. We already know how to do this using the power rule, but now it's asking us to do this using the product rule. And one way we can do this is we can split this up into x times x to the 4th. Then we can use the product rule, just like this. Then we can, this thing right here turns into 1. This thing right here turns into x times, use the power rule here, 4x cubed. And then after simplifying, we get that the answer is 5x to the 4th. Okay, before I go on, does anybody have any questions about anything I did? Once again, feel free to call out. I won't really be checking the private chat. Okay. So in that case, if nobody has any questions, I will go on to the next thing, which is the chain rule. So we know how to differentiate x squared times the sine of x. But what about a function that looks like sine of x squared? So when we have one function inside the other function. And okay, this looks like a bit of a mess, but firstly, what we do is we treat this as one separate function, and we want to differentiate this with respect to x. And so this definition of a derivative actually comes in handy. We don't actually have to do this derivation using the traditional method. So if you want to find the ratio between a tiny change in this big composite function to a tiny change in x, what we first do is we can set up a ratio between this big function and a tiny change in the innermost function, and then we multiply that by a tiny change in the innermost function over a tiny change in x. And what happens here is that these tiny changes in the innermost function, they cancel out because one's in the numerator, one's in the denominator, and we get our original fraction here. So while this seems to make things more complicated, it actually doesn't, because it actually makes life much simpler. So what this is telling us is this first factor right here, that's basically you taking the derivative of the outermost function and then plugging the innermost function in. So this term right here, you're pretending that this innermost function didn't even exist, that it was just x. You still plug the actual like innermost function into the outermost function's derivative, but this derivative is still taken with respect to a tiny change in this function, this inner function, and not x. And then you have to account for this by multiplying by the derivative of this innermost function. And this is called the chain rule. So this is how this would look like in Lagrange notation. This might look a bit simpler for those who want a bit of a simpler version of this. So this seems like a lot of variables. Yes. Yes, Ria?
What's Lagrange notation?
Oh, so I went over in the 4th introduction to derivatives class how there are many different notations for the derivative. So for instance, this one right here is called the Leibniz notation. The d something over d something. This right here, h prime, f prime, g prime. So that's denoted by the apostrophe. That's called Lagrange notation. And then there's also a third type of notation called Newton's notation.
Okay.
Yeah. So if you want to review these concepts, the slide PowerPoints are available on Classroom. So if you want, you can always refer back to those as I explain concepts. But definitely feel free to ask questions if you are confused about something. Okay, so back to what I was saying, this is a lot of variables. Objectively, this is like a lot of variables. So what we will do is we will say using an example. So if we want to find the derivative of the sine of x squared, what we could do is we can say, okay, so this is the same thing as the derivative of sine of x squared with respect to x squared times the derivative of x squared with respect to x. So this right here, the derivative of sine is cosine. We plug x squared into that. That is all that this first term means. Oh, whoops. Then this term right here is just 2x by the power rule. So this is how we use the a derivative using the chain rule. And once again, there can be many more layers. For instance, we can have e to the power of, or like 2 to the power of sine of x squared. And we would still be able to evaluate the derivative by using the chain rule multiple times. For instance, if this function g of x is composite itself, then we can apply the chain rule to this derivative right here. So basically like a layered step by step, but intuitively what this means is that the tiny changes in g of x are canceling out in this combined product. Okay, so now we know the derivatives of sine, cosine, exponential functions, and then how to differentiate two functions multiplied together and two functions inside each other. Does anybody have any questions about any of that? Once again, if you have any questions, please feel free to just shout out. No questions? Okay, because this is some pretty difficult stuff. We are moving at a pretty quick pace, actually. So if you have any questions, don't be shy. Please reach out, because it'll help me, it'll help you, it'll help everybody. Okay. So now we will actually see these product rules and chain rules in action. So we will combine the two and find the derivative of tangent of x. But some of you may recognize tangent of x is just sine of x divided by cosine of x. And one way we can quickly change this before we get started is we can say that this over cosine of x is the same thing as cosine of x to the negative first power. So we rewrite this because it will be easier to use the power rule when we differentiate, but I will get to that later. So we take the derivative of the tangent function right here. So that's the derivative of this complicated product. So here we have a product. First thing we do, we use the product rule. So here we have the derivative of sine times cosine to the negative 1. And by the way, just to clear some things up, cosine of x to the negative 1 written in parentheses like this isn't the inverse cosine. It's 1 over the cosine. So it's not our cosine, it's 1 over cosine, just to clear up some notation here. So here we have sine of x times cosine of x to the negative first power. And then we add sine of x and multiply by this cosine derivative here. So this sine of x derivative turns into cosine of x. It's pretty simple. But then this derivative, we can recognize this as a composite function. We have one function, cosine of x, inside of another, x to the negative first power. So those are the two functions, and we can take the derivative of this using the chain rule. So this derivative right here, we can write this as the ratio of a tiny change in this big hairy function to a tiny change in the inner function, so cosine. And then we multiply that by a tiny change in cosine of x over a tiny change in x. So that is basically just the chain rule in action. That's all I used here. Nothing really fancy. Does anybody have any questions with this step, because it looks a bit complicated on my computer? Okay. In that case, the cosine of x and the 1 over cosine of x, when we multiply them, they just simplify to 1. This thing right here, since we are differentiating with respect to cosine of x, we can just use the power rule. So the power rule, we bring down the negative 1 and we subtract 1 from the exponent. So we get, and we can do this once again because we're differentiating with respect to cosine of x and not with respect to x. So we can say that this is negative, because this is from the negative 1 being brought down, cosine of x to the negative second power. And then this derivative of cosine of x, we can't forget that. The most common mistake is to forget it, but don't. This is just negative sine of x. So the negatives cancel over here, Then we have a cosine of x squared in the denominator. The two sine of x's make a sine of x squared in the numerator. Then we can turn this into cosine of x squared over cosine of x squared. We can combine it into one massive fraction, and the numerator just turns into 1. So we have finally reached the answer that the derivative of tangent of x is 1 over cosine of x squared. Some of you may be familiar with this being called the secant squared of x. So this is how we deal with tangent. So next week we will definitely be, so we have already studied products, differences, sums. We have studied compositions. There is also something for quotients, and using that rule, it will be much easier to evaluate this derivative. The problem with that rule is that it's, unlike the previous two rules, it's hard to memorize. And because of that, a lot of time you just use the product rule and chain rule with the -1 thing right here to evaluate derivatives of quotients of functions. But if you want to simplify this a bit and you think you can memorize an even hairier looking derivative rule, next week I will definitely introduce something like that. Okay, so this is this derivative of tangent of x. And this is also something that you should probably remember. One of the few things that you should actually try to memorize. Okay, one final thing before we go is to find the derivative of the square root of x. Now, we already have the tools to do this using the power rule. We can treat the square root of x as x to the 1/2, bring the 1/2 down, you get 1/2 times x to the 1/2 minus 1 is -1/2. So the derivative of this is 1/2 times x to the -1/2. But we can also find this using the chain rule. For instance, we can say that since x equals the square root of x, all of that squared, we can take the derivatives of both sides. The derivative of x is just 1. And then here we can use the chain rule. So here we have two functions, x squared, the outer function, and root x, the inner function. So we take the tiny change in big function with respect to tiny change in inner function times the derivative of inner function over x. So in this case, we get this product right here. Now for this derivative, we can just use the power rule. We bring down the 2, it works as normal. And then here we have the derivative that we are looking for, the derivative of the square root of x. And then we can finally bring this 1 over 2 root x to the side here, and we get that this is the derivative. So by the way, if you want to confirm that this matches up with what we did with the power rule, you can always do so. So this is actually a pretty easy thing to show that this matches up with what we did with the power rule. So now I'm going to do this. Actually, how about this? Can you come up with a similar proof using the product rule? I will give you a couple of minutes to do that. And then once you are done, just write done in the private chat or in the public chat, doesn't really matter. Okay, so I'm going to resume my share screen, and this right here. So what I'm asking about the proof using the product rule. it requires a bit of an unconventional application of the product rule. So this proof would require you to think outside the box. What we do here is we rewrite x as root x times root x. This is the same thing as rewriting it as root x squared. It's just that here we rewrite it as a product, while here we rewrite it as a composition of two functions. So here we can obviously apply the product rule. We have the derivative with respect to x of root x times root x. So once again, these two functions happen to be the same thing. They, as you already saw, usually aren't. But this right here is just the derivative of one function times the other, plus that first function times the derivative of the other function. And so here we have two of the exact same terms being added together. That's the same thing as 2 root x times the derivative that we want to find. So we can divide both sides by 2 over root x. We have this 1 over here that all of this mess is equal to, and we get that the derivative is 1 over 2 root x. Okay. So does anybody have any questions so far about anything we did? No questions? Okay, then. In that case, if there are no questions, I will move on to the recap.
For the previous one, why did you not start out with just the derivative of square root x, and you started out with 1 equals derivative of x, which equals derivative of x root x times root x?
Yeah, so that's actually a good point. I did this to demonstrate like one of the ways in which the product rule might be used, and I demonstrated it on a simpler example. This thing right here, I think I could have actually started out with this derivative, but to use the product rule, you need to start out like this. Again, you can. I agree with you that like using the product rule here is kind of pointless, because you can just use the power rule. But on another function, which I don't know isn't the power, we can actually use this application. So we can rewrite some function that we do know, and then we rewrite the square root of it twice inside that that derivative sign. So it's a good question. How I even came up with this. It's like I don't know. It's I guess once you do calculus for a long time, you kind of see stuff like that. But yeah. But this is kind of hard to use the product rule if you just start out with this square root of x. Again, you don't really need to use the product rule, but yeah. But good question anyway. And in general, yes.
Okay, thank you.
Yeah. In general, when you want to prove something, you usually start out with the expression that you want to find. This is kind of like, violates the rules of math and stuff like that. This rules of like standard mathematical thinking. Typically you want to avoid doing a proof like this, but if you want to demonstrate a cool application of something, you might actually want to like resort to this more creative style of proof, I guess. But you notice that for most of the other proofs that I include in this slideshow, I actually don't do this type of stuff. I start with the statement I want to prove first, and then I move on from there. But yeah, good question, and definitely a good catch. Thank you about that. Okay, so we are done with our presentation, with our lesson. Here is the recap. So we are now able to differentiate many functions that are not polynomials. We can still not differentiate all functions that aren't polynomials, but we have most of the basic types. So firstly, we derived 2 of the most important trig functions. So we have derivative of sine of x is cosine of x. The derivative of cosine of x is negative sine of x. This negative sign often throws a lot of people off, but it's there. Yeah. And then at the end, we derived another very important derivative of a trig function, which is 1 over cosine of x squared. Once again, we were able to do this using some of the rules that we learned later on, like the power rule or the chain rule. Okay, and then we also looked at derivatives of exponential functions. So exponential functions are special because their derivatives are always constant multiples of the actual functions themselves. So in this case, in the case of any general exponential function, its derivative is the natural log, so log base, our special new all-important constant e, times the actual exponential function. And then a very special thing happens when this natural log of a goes to 1, or when a equals e. And in that case, the derivative of e to the x equals e to the x. So once again, e we defined using our like weird limit thing at the beginning, but this is like a very important application of this constant. And honestly, if you ask a mathematician, he or she would most likely recognize the constant e from this statement right here than from the limit statement that we talked about when deriving this proof. So this is the only function that is its own derivative, other than constant multiples of itself, which is actually a pretty cool fact that such a function even exists. But it does, and that is e to the x. Okay, and then we also found the product rule. If you multiply two functions together, their derivative is f prime of x g of x plus f of x g prime of x. So it doesn't work the same way as addition does. So it doesn't work as f prime of x g prime of x equals. Okay, so live transcription. I don't know if you misclicked, but do you need like a closed caption for a future meeting? Because if you want, I can turn that on. Do you want me to turn that on for future meetings, or is that okay? I guess that was a typo then. Anyway, and then we also have the chain rule, and the chain rule helps us deal with compositions of functions. So this is a function like f prime of g of x times g prime of x. This is how we deal with these types of functions. And once again, all this means is you take the outermost function, differentiate it, forgetting that it's a composed function, and then you plug in the innermost function for where you would usually put x, and then you multiply all of that by g prime of x. And once again, this is all justified very conveniently by our little tiny changes, numerator and denominator canceling out type of proof. Okay, so this is what we did today. We can combine all of this, of course, with what we did yesterday to find derivatives of a lot of different functions. And tomorrow we will, not tomorrow, on Friday, when yesterday's class's homework is due, we will talk about the quotient rule. We will talk about some other like inverse function rules and stuff like that. So yeah, that is it for now in terms of the lesson. So does anybody have any questions before we get started? Before we close the meeting, and that's it for today. Does anybody have any questions about anything? Homework? No? No questions about the derivative homework from 2 classes ago that was due today? No? Okay. If you need anything, you can always call out within the Zoom meeting. You can email me, or if you think that your question will benefit others, you can also type a public post on Google Classroom. Okay. So that is it for today, and I'm excited to see you on Friday. So that's in 6 days. Okay, have a good day, everybody.
Thank you. Goodbye.
Bye.